Hey guys. Uh, I'll start off the video with this. If you haven't heard, I am trying out a new type of stream, and you can find information about it on its community tab. I'm gonna not talk about it here because I already have enough, but you can read about it here. So yeah, I'm excited to do that. But at the same time, right now I'm even more excited to do this contest, AtCoder Beginner Contest 182. And as you can see right now, it's 7 a.m. And in fact, all of these contests are going to be an hour earlier now because daylight savings exists, but only like for us or something. So it just kind of sucks. But that's going to make things fun. It's even earlier now. So the delirium you may have seen me get on previous AtCoder contests is going to be even worse now. How great is that? Yeah. So plan today is just to do this contest. I'll do more stuff tomorrow. And I'm gonna leave it at that. Not really sure what to say. I guess we'll just get started. Yeah, this is unrated for me, so not exactly that focused on it. Okay, this is just like figure out that's just the maximum number of users minus your own, because it's just kind of the definition. So it's, let's see. What is this? You're currently following A users and B users are following you. What? 2 times the number of users following you. That doesn't, okay. I don't understand that. Is that input messed up, or am I just like high right now? I'm just gonna read off the samples anyway, because it's not that big a deal. Does that make sense? Wait, you're following A users. Shouldn't it be like, this doesn't make sense. Well, okay. I assume they just messed up the numbers themselves, and that everything else is fine. Yeah, sure. Okay, I'll figure that out later, I guess. Gives an integer sequence, let the GCD-ness be the number of, okay. Find the integer with the greatest GCD-ness. Alright, we could just straight up do this. Like, just try all possible values of x and see, find the integer with the greatest GCD-ness. Oh, I see. Okay. And I++, C and AI. Yeah, if there are multiple integers, anything's fine. So we'll just try all possible numbers, and then count the number of elements divisible. Aj mod I is equal to 0. Best equals max. Oh wait, this should be pair, not max. Best, and make pair of count and the number itself. Then print that. 3, 9, 1,000. This makes sense, right? Yeah, this does make sense. Okay. Sure. We're going up to 1,000 from 2. Given as a positive integer n, where none of the digits is 0. I'm going to make a multiple of 3 by erasing at least 0 and at most k minus 1 digits from n. And concatenating the remaining digits without changing the order. I hope the audio is fine, by the way. I think I made it slightly lower, but I don't know. Wait, what? Erase some digits and concatenate. Yeah. Is there any smooth way to do this? I mean, you could do casework on everything, and that's fine, but I kind of just don't want to. So what I'm going to do instead is overkill it with knapsack, and that's totally fine. So we're going to read this as a string and then treat this like character by character. Oh, wait, you need to do the minimum. Okay. Alright, fine. So we'll do the count. Keep a count of like the numbers of characters mod 3. So if we're already done, then we're already done. Otherwise, if we have 1, then either if count 1 is greater than 0, then we can just remove that one. So let's do that. Otherwise, if we have at least 2 of the 2's, then we can also do it that way. So count 2 is greater than 1. Otherwise, there's no combination of 1's and 2's we can do, so it's impossible. And then the same thing applies if total equals 2. So if count 2 is greater than 0, that's exactly what we need. Otherwise, we can do it with at least 2 1's. Otherwise, it's not possible. That is the idea, I think. What? 35, 0, 1. How'd this work? So it'd be like 2, 2, 2, 2, 2. What? That's 10. What's happening there? How is total? Oh, the total is 1. So if count 1 is greater than 0, how is count 1 greater than 0? Oh, shoot. I should, yeah, initialize the array. It's a good idea. Okay. I assume the rest of the answers don't change. Is this about A? It is about A. Okay. Oh, we did get it wrong. Nice. How wrong? Ugh, why do they give problems like this? Okay, so what's happening? We take the total, and the digits in n is 0. Okay, that just means there won't be leading zeros. That's useful, I guess. Should also be 2. Sorry, another clarification? Okay. In this case, it is impossible to make a multiple of 3, so we should print -1. Don't I have that? Let's see. 1, 3, 1, 4. Oh, because it's, okay. Guess that could make it remove all the digits, and that's not useful. Guess we also want to make sure that we don't remove too many. That's fun. Somehow it just happened to work on that one? Or did I do it wrong? Did I fail the sample and not even notice? Oh, I actually did. Nice. Okay, I guess that's a thing. As you can see, I'm in great shape right now. Wait, this is right? 1, 0, 1, okay. Alright, given as a number sequence. On number line, there's a robot at coordinate 0. Move A1 in the positive direction. Move A... Yeah, I see. Alright, so say you're at some starting point, like, expand this out. Say you're at some starting point x, and then you have some sequence like, for example, like this, and then like this, or say like this, and then like this, for example, and then you would keep going. Then the farthest that you're ever going to get in this sequence of operations is essentially the like the maximum prefix of values that you have, because these can be negative, so you might move to the left, but it's going to be this prefix of values that you get. So you're interested in the maximum prefix, like the maximum sum of a of 1 to some j, for j being less than or equal to like the I you're solving for. So you can find the maximum prefix, check the answer with that, and then you can like simulate just making all these moves by summing up their changes in coordinate and then doing it all at once. And then you can find the maximum prefix for the next one and kind of just keep going. That is the idea. I feel like it's easier than the previous one because the previous one's some casework stuff. I don't know. Hmm. So we start 0. Keep track of the maximum prefix and the sum of the prefix. Sum plus equals AI, max equals max, max AI. And keep track of the current coordinate too. Ants equals max, ants cur plus max, because that's how far we can get in this sequence of moves. And then cur plus equals sum. That just means we move by that sequence of moves. And somehow that's wrong. Epic. How exactly? -2. Oh, this should not be 0. What should it be? -1e something. 17. We can assume this is 0 because we automatically started 0, but this has to be smaller because the prefixes can be negative. What? 5. Still 3. Epic. I don't understand. -2, -2. Move this back here, I guess. So 0, -2. Alright, then -2, 1. How is that? Oh wait, this should be sum. Yeah, because that's the prefix itself, not the array element. That was dumb. Okay. How did that even get the first sample? Interesting. I guess because it happened at the beginning or something. Everything look fine. Scene to end, reading the array, make the max tiny. For each thing, take the sum, take the maximum, consider it, and then move. Makes sense. Whatever. If we get penalty, again, can't hurt that much more. A grid with H rows and W columns. Let square ij be the obvious thing, just the position. There are n bulbs and m blocks in this grid. The ith bulb is at square AIBI, and the ith block is at square CIDI. There's at most one object, a bulb or a block at each square. Every bulb emits beams of light in 4 directions, up, down, left, and right, that extend until reaching with a square of the block, illuminating the squares on the way. A square with a bulb is also considered to be illuminated. Among the squares without a block, find the number of squares illuminated by the bulbs. Interesting. Or square with a bulb? Is that what I said? I'm not sure. Okay, well, H and W are small. That's cool. So my idea is something like this. Let's do the rows and columns separately and just like figure out what's illuminated. So assume we're solving the 1D problem where you have like a block here, maybe a, I'm not going to use yellow. Let's say bulbs are blue, and you have some empty spaces here. And my idea basically is to do some sort of 2 pointers thing where we basically say we start here, we find nothing, so we continue. but then like we maintain that we're still like the left point of the segment we're in is here. And then we go here, we find nothing. We go here, we find a bulb. So now we know we can light all of these up. And then now we know we have a bulb, so when we go here, we still have this bulb. So we just kind of keep going. Then when we hit this block, we recognize that we can't use this bulb anymore. So we like continue the 2 pointers sort of thing, and then we just go here and do the same exact strategy. Then when we hit this, we'll fill all of these, and then this pointer will move to the current place, and then we'll use this bulb until the end, and then we just label all these. And then we'll do this separately for rows and columns, and then like it'll be on the same grid, so it's just gonna work out in the end. Yeah. How does the input work? Okay. B for bulb. Another clarification? There was a problem with the statement. Okay. Bulb block. I'm gonna use the scripted variable names now because I cannot guarantee that I can stay focused enough to remember what I'm doing myself. Okay. So int state and use 1 to represent bulbs, and then use 2 to represent blocks. Then we continue. By saying, alright, for each row, initially we aren't lit, start equals 0. If we're at a block, then start equals the position after this block, and we're no longer lit. Let's see, while start is less than j, lit I start equals 1. And then once it's equal to j, then we don't really care about it anymore because we already know that we have, this should be on. Then lit equals true. If lit and state ij is not equal to 2, then on ij equals 1, because that's what we have. I think that makes sense. We kind of just do the same thing for rows. I'm going to rewrite it to avoid copy-paste errors. Because there are many copy-paste errors and it's very dangerous. Let's see, state j is the row now. J plus 1, lit equals 0. Else if state ij is equal to 1. Most of this is the same, just want to be careful. On start I equals 1. Lit equals 1. Now see, this is the problem. This is the problem with copy-paste errors. You miss things like these. State ji is not equal to 2 on ji equals 1. Let me just count the number of things. see how this goes. 7, 8, 24. Let's see, is this alright? On, state, bulbs and blocks, sure. Rows and columns. Set the stuff. Set the start. Do the 2 pointers thing. This is all O of n. Because start is monotonic. After that, it's the same thing, but avoid copy paste errors ideally. Well, start is less than j. Yeah, okay. Ideally that works. Assume this is the hard one now. Okay. N kinds of coins are used. A1, A2, up to AN, which is strictly increasing. A1 equals 1 holds. Yeah. AI plus 1 is a multiple of AI. I am scared of this because I've seen something that's kind of similar to this, and I hope it's not that. At some shop in this country, London the dog bought an X yen product by giving Y yen to the clerk and receiving the change of Y minus X. Is Y minus X fixed? Minimum number of coins needed to represent those amounts of money. I have seen a problem like this, and I didn't know how to solve it, so that's fun. I'm not exactly sure how to do this. I guess I'll try again at the optimal time. Why not? In X, find the number of possible values for Y. So I guess it's not exactly, it's greater than or equal to, which is kind of an interesting point. Both Lunlun and the clerk used the minimum number of coins needed to represent those amounts of money. Additionally, the clerk did not return any kind of coins that Lunlun gave. So, okay. So what that means is that, like, it's the minimum number of coins. So I guess the idea is, say you have 2 coins, like 1 and 5, and then you have a money amount like 17. Then you wouldn't do something like you would use 3 of these and then 3 of these, because that's a waste. You can instead use 2 of these and 3 of these, I suppose. Because the clerk did not return any kind of coins that Lunlun gave him, so he could like return the 1, and we don't want that. So either what happens is we do a 2 and a 3 here, or we ignore this, and then we decide to do 0 here, and then we would need 4, I guess. So what we're kind of really interested in is, when we get to this point, how many of these have we used already? I think that's the question that we're asking. How many of these do we not need to use anymore? Does that help at all? How would you even do that? Okay, so say you have like AI and AI plus 1. The number of coins of size AI you would use, like the count of AI, is less than this. Because otherwise you can turn all of these coins into a single AI plus 1 coin, and that would be pointless. So don't do that, and instead, that also means that the total value of these coins is less than a single one of these. But it can get very close, I suppose. Oh, but if the total value of these coins is less than a single one of these, then that also means the total value of the previous coins is less than a single one of these, which means that the total value of all of these coins is going to be less than a single one of these. So essentially the question is, when we get to here, have we made enough things to be able to like miss out on using one of these coins or not? Now how would you measure that? I guess it's kind of like, did you use the previous one? No, it wouldn't be that simple, would it? It wouldn't be did you use the previous one. It would be something like weirder. Oh wait, it's the number of values of y. Oh god. How many values of y could there be? So we have a bunch of powers of 2, right? Then there are like problems. Yeah, then we can do anything. Oh wait, actually, no, never mind. We're creating like a weird, like, it's not like a base k number, but it's like kind of like that because all of these numbers aren't going to interfere with each other. Like the amount of things we take here isn't going to interfere with this since the numbers are less. So it's kind of like whatever we do here isn't impacted by the specific numbers we take here. So we can kind of combine the answers without worrying about intersections. That's what I'm saying. Like the intersections of the values of y won't be a problem. This is like weird though. So why can't you do something like 199 here? Alright, it could be 198 itself for this one, I'm thinking. So the direction that seems to be right here is some dp, where it's dp of I and then used, I guess, where it's the number of y values where you've used the first I values, and used is a flag that represents this. Have you used enough of these to make it so you can skip this one or not? So my question is, does it even matter? I think it does. Does it? It should. Either you do use something or you don't use something, and that creates possibilities. Okay, I'm gonna be right back. I'll think about this in the meantime. Okay, I should take what I said back, by the way. This is not the same problem I was thinking of before. So, props to AtCoder. It's fine. So, like, what does this do? What does this DP do? Say you think the idea would be something like this. You have AI minus 1 or something, and then AI, maybe AI plus 1. Maybe this doesn't matter. But, like, what's the value? It's like x, right? Consider x mod the next value. If we're computing for AI, consider x mod the next value. So x mod AI plus 1. If it's less than AI, then it's possible. Wait. Okay, this is 1, so that's important. If it's less than AI, then if it's less than AI, then it's possible to do this. That is, it's possible to totally ignore using AI. So the question we have when we get to AI is, I guess, could we have made a number larger than x mod AI? Does that question even matter? I think it does, because we're asking, can we skip AI? Are we allowed to do it so we don't use it, I guess? Okay, I don't think I entirely understand this. I guess. Alright, it's just no excess. Wait, is it asking can the change be represented as coins that aren't that? Is that what it's asking? Is that like a requirement for it? That doesn't make sense. Why can't it be 120 here? Is the question. Is it like an unnecessary thing? Oh, I see. I think we can kind of avoid that condition by just saying like use as much as you can. I think that's the idea, right? Is that the idea? Alright, come on. This is like a struggle. I think this is all about details. This feels right. I just don't know how to do it, is the question, is the thing. So we ask, can we use these numbers to get a number less than or equal to x mod AI? It feels like some weird sort of digit DP, maybe, where we ask, it's like digit in a very strange sense of the word. What are we even checking? Essentially, here we have two choices. I don't think we want a number greater than or equal to. We want exactly equal to. Otherwise, we would reduce some of the numbers here because they would be pointless and kind of a waste. And the only time we actually consider numbers that are greater than x mod AI is when we're like finishing, when we're on the last number that we're using. I feel like that would be important. Still weird. 9, 10, or 14, huh? It's like a strange set of conditions. I guess for every number we consider whether it can be the last one. Okay, this is not going anywhere. Asking for the amount of numbers where you have some like thing that's equal to x mod AI is the same as saying, I guess, like say you come into here and you already declare that you don't have x mod AI, then the same here, you're not going to have it here because you just like can't, based on just AI minus 1. But if you do have it, then the question is, how many times is it going to like be equal? And if x mod AI minus 1 is like It's like some division thing. If, I guess it's like, it'd be this. If x mod ai is less than ai minus 1, then you can get away with taking none of these. Otherwise, you would have to take at least one of these to maintain the equality. So this dp would sort of be like dp of are you here and are you equal. And then the like pushing it to the answer would be any number that's greater than any number that's greater than this, I guess. Maybe the number of times you're equal combined with like the number of times you aren't. If you aren't equal, say you already aren't equal. I'm trying to work out the transitions now. If you already aren't equal, you're coming in like this, then what do you want to do? I think you don't want to take anything. Is that how that works? Because if you do, then like it's going to be pointless, I would guess. You either wouldn't want to take anything. Could you be more too? Would there ever be a point where you would want to be more? But that would give you excess. And excess is bad. Like, I don't think you'd want to be greater, because then when you finally form the number, there'll be waste. Or would it be? See, like the numbers like this, 1, 4, and 1 equals 2 or something. If you took 2 of these, then you can also... No, you wouldn't be able to take this, I guess. If you took 3 of these, then you'd always have change. You'd always have change, because this is like a multiple, and you can't take more, I guess. So these transitions are weird, is the basic idea. Let's see. So Cn to n, and then we use k to represent that. Actually, let's just be normal and use that the things. And we initialize dp like so. So dp having used no elements, and because it would be equal. Base case would be dp 0, 0 equals 1. Do we care about 0, 1? Well, we can't be not equal. Let's represent 0 as equal, 1 not equal. Actually, let's do it like 0 is not equal and 1 is equal. Then we would be equal here. Now, val equals x. If I is less than n minus 1, val mod equals ai plus 1. Because with the last element, we can use as many as we want of it. So transition is, if we're not equal already, then we don't take anything. Because if we do, it'll be excess later. If we're not equal, we're assuming we're less. Why would we have taken it in the first place is the question, I guess. Indeed, why would we have? I suppose it can't hurt as long as we don't leave residue of the same thing. How would this work? This is messy. Oh, these samples are not helping. Okay. Come on. If we're already not equal, what do we do? Are we allowed to take the next one? Like, say the number is 144, and the current number we have is 4 for some reason. Then we could either take this or not. I don't think it matters. So we have, say, 4, the 1, 20, and 100. So if we take the 20, then we'll be at the point of we could take 40, or we can take nothing. And if we're not equal, we can do something like taking 60, or we could take nothing. And both of those would work, I imagine? Because 160 would be valid, yeah. 144 would be valid. 204 would also be valid. That's if we are equal. Let's say we aren't. Then it would be like, if you can, take more than usual of these. So maybe it is possible to be greater than. I think that's another case I guess we have to consider. So we have less than, equal than, and greater, equal to, and greater than. Because we could have something like this being 60 or so. So maybe this is 3 states. Do something like 3 times x. Make it not interfere. Maybe like 3 times AI, I guess. Something like so. There's just an upper limit on the number of things we can use. So then the limit equals next val over AI. And the requirement equals val over AI. And there's some casework we gotta do based on this. So if this is this, right, then this requirement will be 0, and then no matter what we do, we don't want to take anything? No, that wouldn't be it. It would be something else. Wait, is there a mod here? There's not, because it's not that big a deal. This can't be ordered through to the end, because they gotta, like, they give the... There aren't that many possible values of y. What's order 2 to the end? Should be fine. Yeah, it's about, like, the same thing. So if this is true, then if we're less than... Either we take this value or we don't. If we don't, then we're still less than... How less than are we? This feels quite messy. I'm not sure how to do this. Why is this so hard? It should not be this hard. Oh. So if we're already less than, then this is going to be very hard to follow in a screencast. I will explain this better later. I just realized, but just want to work this out for myself first. Ideally solve this before the contest ends, although I'm not sure if that's even going to happen. So here we either take nothing, and then obviously we stay less than. And that's fine because this doesn't we assume the change would already work out so that we don't violate the condition. And if we take nothing, then we haven't used this coin, so we still do that. Or we take something, and then this something, if we take this something and we're still less than, then it has to be like the exact value of this, the x mod AI plus 1 divided by AI. The exact value of requirement, otherwise we'll be screwed, like it's not possible to do so. And maybe we also take x plus 1, and then we'll end up greater than, if this is possible. Now what happens when we're greater than? Does that screw us over? Well, when we're greater than, we also assume the change is going to work out. And the change will work out as long as we don't get too high. And we wouldn't get too high if we take exactly one more. So this is a possible transition. Okay. And then for here, either we take nothing, and then we stay, either we take nothing, and either we become less than, or we stay equal, depending on how this works. Or we take x, and we stay equal. And we don't want to take anything higher because that will make the change screwed up. That's how that would work, right? Would we be able to take 0? We could, because then it wouldn't screw us over, I suppose. Or we can say we're greater than, and then if we take x, we're still greater than, and the change will still work out. If we take 0, now we're less than or the same, depending on if 0 equals x, and then we'll be less than. And we don't want to take greater because that will screw us over. Okay, sure. So if these two are equal, then no matter what, let's see, dpi plus 1, 0 plus equals dpi 0. How'd this work? dpi plus 1, 1 plus equals dpi 1. dpi plus 1, 2 plus equals dpi 2. Else, now we have more options. So dpi plus 1, 0 plus equals dpi 0. But at the same time, we could do this in two possible ways. Taking that or taking that one. So this should be 2, I think. And then this would say, how exactly would this work? It would say dpi plus 1, 2 plus equals dpi 0. Actually, this depends on if rec, how does this work? Limit is a exclusive limit. So if rec plus 1 is less than limit, then we could take that. Then we do equal. So dpi plus 1, 1 plus equals, alright, dpi plus 1, 0 plus equals dpi plus 1, 1, or dpi 1. And we also take the equal amount. And we do the same thing for 2, except it's just 2 instead of 1. This would go there, this would go there, and this would go there. And this, actually this is kind of on its own. It doesn't depend on if they're equal or not, so we'll leave that here. And then consider x over ai if this requirement is less than limit. No, it would be requirement, right? Or it would be limit. Then either being greater than or equal to would be fine. So ants plus equals I plus 1, 1 plus dpi 2 should be I. How'd this work? We want to consider I plus 1, don't we? And this should be I plus 1, I guess. Because this is after we consider this number. No idea if this works. Makes sense in my head. Although the transitions could very well be wrong, and that's acceptable. And we get a floating point exception. So AI is 0 somehow, because I haven't actually read in the array. That makes sense. So we get 5. Do we overcount everything? We do indeed. 7, and this is gonna be huge, I imagine. Yeah, okay. Alright, what's with that? So let's just print stuff. It's very likely the case that these transitions I have are just wrong entirely. So 1, 1, 0. How's that? So we can either be less than by taking nothing, less than 4 by taking nothing, or equal to 4 by taking that. Then at 5, we could be less than interesting. We don't want to count the same value twice, I guess. So we can obviously just let's try this. Is this exactly 1 over every time? It is not exactly 1 over. Okay. So here's some problems here. What will be this issue? So we get the 3 here, right? But like that's not right exactly. One, 5, 10. So 1, 1, 0 would be right. How do we have 3 ways to be less than now? So either we have 0 or 4 is the way these numbers work. So if we have 0, we could take a single 5, and then we would have 5. And that would be possible, and we would still be less than, but it would work out. Or we could take nothing, and we would have 0, and that would also work out. Or from having 4, we could take nothing and have 0, and have 4, and that would work out. Or we could take 5 and have 9, and that would be an answer. We have no way to be greater than. Okay, and then, so currently we have 0, 4, and 5. Which one of those is invalid? That would be 15. Okay, what are we miscounting here? So if we have 5, does that violate something? Well, we still have less than the number. But like it runs into a problem later, doesn't it? What kind of problems do we have? Why would we not count this? Because I mean, later when we add a 10, we'll get 15 and it'll be bad, but why would we not want to count the 5? Is my question. If it's on like 9, it would be fine. Maybe this is a bigger problem than I thought. So 0 and 4 are okay to keep with, because like being equal is fine. Being greater than would also be fine, but somehow this specific instance of being less than is like a problem. Maybe we don't want this transition. Maybe we only want this. Does that work? It actually does work. Almost. Still wrong. Closer though. Problem D. Fine. Okay, what happens with this one? I guess we wouldn't want that transition because that would kind of screw us over, maybe? Is that how that would work? Depends on what the change would be, I guess. Because we have this leftover. Like if we have 1, 5, 15, that would be the same issue, wouldn't it? Not even sure if it's possible to solve it this way. Okay, what's going wrong here? There's one way to be equal, there's one way to be greater. Somehow we're getting that there are 3 ways to do this. Maybe we do something like this. Because once we're greater, then we don't want to use this anymore. That makes it work. Do we want to do the same thing for equality? I guess the answer is no. Alright, submit first, think later. Probably got wrong answer, that's fine. I'll figure out what's wrong with it after. Okay, I guess it passes. Where are we in standings? Imagine not great. How many people saw this? Many, okay. So yeah, I was slow on this. I guess that's fine. It's not rated anyway. Blame it on the earliness of the contest, I guess. Details are hard. Because this was just kind of like, once you figure this out, it's just work out these transitions. Okay, let me make sure I understand what I'm saying before I say it. So we wouldn't want to do the same thing for equal, because like equal just like has its own definition. But if we're greater than, and we can take all of these greater thans into the answer, then we can't like build off of these greater thans. Because that's pointless. Okay, that makes sense. But for equal to, it's like not a problem. Sorry, I've just been like wandering around thinking about why that works. Don't actually understand why that works. It does work, right? I mean, it does work because it passes, but it makes sense, right? We take equal. We wouldn't actually consider it anyway. All we're interested in is greater than, because like the way these numbers work, we can always get x. We can always get exactly x. which means we don't actually care about these states in terms of the answer. The only states we care about are the ones where we're greater than the current like prefix. And therefore, even though we don't also set these to 0, which we might want to, it's like not that big a deal. Okay. I'm going to try to explain solutions now. F might be a bit of a struggle, but I will do what I can. But I have nothing better to do anyway, so I'll just go over everything I can. I mean, everything. So I did solve everything. I'll give myself that much credit. A user following. Okay, so this problem is basically like to do what it tells you. So first, figure out the number of users that you can follow in total, which is, what would it be? 2 times the number of users following you. So A, 2A plus 100. This is the total, this is the maximum number of users you can follow. And you're currently following B. So the number of users you can, like the number of extra users you can follow is just the number of times you can increment B to get this, which is just like the maximum number of followers minus the current. And that's the answer. And because like you have this constraint, this number is always positive, so you don't really have to worry about anything. But the answer is just that. Let's see. Okay, so let the GCDness of a possible integer k be the number of elements among a1 to an that are divisible by k. Find the integer with the greatest GCDness. Okay, this problem is called read the constraints. N is 100, AI is 1,000. That means you can straight up just try all possible k. Like, fix some k, and then go through all AI. And then if AI is divisible by k, increment some counter. And then over, like, a simple way to do this is to store pairs of, like, the count, like the GCDness and the value itself, and then take like the maximum over these pairs where you consider this element first. Just basically any element with the maximum like GCDness, you just consider all the elements, compute their GCDness naively, and get the best one. If even that's confusing, you can check my code, I guess. But it's just straight up do what the problem tells you to. Okay, problem C is to Problem C is to do some annoying casework. You're given a string, or you're given a string, which I guess is a number, but it doesn't really matter. Like this tiny, like for example 369. So it's a bad example. Let's do 35. What you can do is you can remove some of these digits to make it so A, the number must be non-empty. That means you can't remove all of them. And B, the resulting number must be divisible by 3. Find the minimum number of digits you need to remove. So the first part is, for a number to be divisible by 3, the sum of its digits must be divisible by 3. These are equivalent, meaning that if the sum of the digits is divisible by 3, then the whole number is. And the whole number is divisible by 3 only if the sum of the digits is. This is like a very well-known thing, but I can prove it right now. So consider the sum of the digits. It's like, say you represent a number as like a n minus 1, a n minus 2, etc. And each of these numbers is a digit. Then it would be the sum from I equals 1 a1. It would be the sum from I equals 1 to n of ai times a power of 10 that represents the like position in the number. So 10 to the n minus, or 10 to the I minus 1. Okay, but consider this sum modulo 3. 10 mod 3 is 0. Or 10 mod 3 is 1. Meaning that like, this is the same as saying the sum of ai times 1 to the I minus 1. Which is obviously just the sum of ai. So this is the value of the number, and this is the sum of the digits. and modulo 3 they're equivalent, which means that if one is divisible by 3, then the other is, and vice versa. So that's the proof for this well-known concept. And if you didn't know that before, now you do, because it comes up often. You should probably know it. So now that we have that out of the way, how do we make it so the sum of the digits is divisible by 3? Well, let's first take the sum of the digits. Let's say 8. And then 8 mod 3 is 2, and we want to make it equal to 0. By the way, a number is divisible by another number. A is divisible by B if A mod B is equal to 0. That's also a well-known fact. Not exactly sure how to prove that one. It's just fundamental understanding. But let's take 8 mod 3, and it's 2. Okay, now there are, let's call this number k, the residue of the remainder of the sum of the digits mod 3, or divided by 3. So k is the sum of the digits mod 3, right? I am speaking articulately. Actually, it could also be just n mod 3, either way. Let's say k equals 0. Then the number's already divisible by 3. We're done. So automatically we get 0. Otherwise, let's say k equals 1. Then there are two ways we can do this. We can remove, so if we remove anything that's 0 mod 3, then it's not going to help us, so let's assume we don't. And what we instead want to do is count the numbers ci, which is specifically c0, c1, c2, where c0 is the number of digits that are 0 mod 3, c1 is the number of digits that are 1 mod 3, in this case it would be none, and c2 is the number of digits that are 2 mod 3, which an example would be 5. Then this helps us because we need to use only those facts about the digits, how much they affect the sum mod 3. So k equals 1. If c1 is greater than 1, so there are three possibilities. If c1 is greater than 0, we have at least one number that's divisible by 1. And at the same time, n must be greater than 1, because otherwise we can't remove the only digit we have. If both of these are true, which means we can remove a digit that has residue 1, then we could decrease this by 1 to 0, and therefore the answer would be 1. Otherwise, there's only one other way we can do this. If we don't have something that's residue 1, then all we have are things with residue 0 and residue 2. Residue 0 doesn't help us, so we only consider residue 2, and it takes at least 2 of those to be removed to make that happen. Because we would subtract 2 twice, and then that would be equivalent to getting 4, and then negative 4 is equal to negative 1 modulo 3, and we want to subtract 1, so that's what we want. We need at least 2 things that are residue 2, or remainder 2. So if C2 is greater than 1, and n is greater than 2, because now we're removing 2 digits, then the answer is 2. And otherwise, it's impossible, because we just tried both things, and we can't do either of them. And so if k equals 2, it ends up being basically the exact same casework, but you swap the zeros or you swap the 1s and 2s. I'm not going to delve too much into why, but you can work this out for yourself. Basically, it comes out to C2 is greater than 0, and n is greater than 1, then the answer is 1. If C1 is greater than 1, and ampersands, I'm actually surprised I've drawn these so well, then you get 2, and otherwise negative 1. So this is the sort of decision tree of casework for this problem. So right here, you can just straight up write the code out of this. Yeah, okay. So that is C. D is kind of fun. So consider that you're at some position X. And say we've say we're at turn I, which means that in this turn we're gonna do A1, A2, all the way up to AI. We're gonna move those amounts. And assume that we've already solved for all the things less than I. So we already know the answer for that. Actually, we'll just find the answer for all I, and then the big answer is the maximum over all of them, since like considering all I just considers all possible locations, or all possible like times. So let's solve a single value of I efficiently. How would we do this? Well, we're going to move something like this, and then we're going to move something like this, and then say something like this, and we want to find the farthest to the right we are. In this case, it will be here. Yeah. But more generally, let's consider only this, only like this sequence, this singular turn of I again. And then let's say we consider the position J that we're at, where we just did A1, A2, ... AJ, where J is less than or equal to I. Then at position J, we've essentially moved A1 plus A2 plus A3 plus all the way up to AJ. J is less than or equal to I. And that's the same as saying we moved like the prefix of the first J operations, because that's just what it is. Right? And so to find the farthest we're at, it's equivalent to saying, of all of these like prefixes we've moved, what's the maximum over that? And then the answer for this specific I is the starting position plus the maximum over all J of, it's like the maximum of the prefix sums, essentially. So A1, well, it'd be of this. That'll be the answer for this I. So it remains to just find this efficiently. First of all, we can maintain x as we go along, because x changes each time by just the prefix of, like the sum of the ith prefix. And so you can take prefix sums by using the fact that like, let like pi be the sum from I equals 1 to n of ai. Then pi is equal to ai plus p of I minus 1. Because this is the sum of a1 to ai minus 1, and then to make it the sum, this is the sum of a1 to ai minus 1. This is not a minus sign, this is like 2, and then this is a1 to ai, and so the only difference between these is this element, which is why we add it. So using this formula, we can compute all pi in O of n, like at the beginning or however you want to do it. And then this is equivalent to saying it's the maximum over all j of pj. This would be j is less than or equal to I. But this is also like another prefix thing. It's the maximum of the first I prefix sums. So if we consider the same thing we just did for prefix sums, we can use the same formula for prefix maximums. We say like, let mi be the maximum of the first I prefixes, then it's the maximum of pi and mi minus 1. By the same argument, this just works because this is the only difference between these two. So it's x plus mi. And then the answer, the overall answer, is just the like the maximum over all possible x plus mi. And again, to find x, you just like, as you go along, you just apply the sum of the prefix of I. So I mean, we can continue bashing out this formula until it's all in terms of ai, but like x is just obvious what it means. It's the coordinate that you start at before applying the ith sequence of operations. And of course, this begins at 0 by definition, so you just maintain x, maintain mi, maintain pi, and check everything. Because again, this solves for a specific I, and we're solving over all I. Yeah, okay. I'm not sure how clear that was, but I tried. Yeah, I did try. How are we doing in standings? I assume we went down because of penalty, but shouldn't have been that bad. Okay. I mean, it's not a terrible rank. I suppose I've done worse. I've done better, but I've done worse also. So that's fine. Okay, this one's fun. So consider a bulb. I'm gonna make bulbs blue again, same color scheme as in the solving the problem. Then this is going to affect everything on its row and its column, and we want to find how many cells are affected by a bulb. So let's consider only this bulb, right? It's not going to affect like anything in this region. It's only going to be its row. So the naive solution would just be to like have this, like naively apply this bulb to all of these cells to the left, right, up, and down, and just like do it. But that's not going to work because the constraints are too big. But like the idea is each bulb is independent to its own row and column. Which means that when we're considering some cell, let's say we're solving for this cell, I'm going to use a triangle for some reason. Then what we're really asking is, how do the bulbs on the same row and the same column affect it? There are a lot of ways to figure that out. The easiest way, or the way I found to be easy, is to solve for each row independently of the other rows. So we're only considering this row now. So this is like a 1D problem. And then we'll do the exact same thing for columns. And if this thing is like lit by either of them, then we'll be happy. Let's solve for this row. And let's just like find like all of the lit cells on this row by bulbs on this row. So like this bulb is going to affect this whole range. And then whatever is on the ends of this range is not going to be affected because there's a blocked cell here. But the idea is like we can do a strategy like 2 pointers, where we say we keep track of the section we're in, where each section is like blocked off by the block cells. For example, like this would be a section, this would be a different one, this would be a different one, this would be a different one, just separated by the block cells. So we say at the beginning of the section is here, and then we look here. There's no bulb, and we haven't had a bulb before, so this is not lit. Then we go here. This is not a bulb, we haven't had a bulb before, so we're not lit. Okay, we hit this block cell, which means now the new beginning of our section is after this block cell. If there's also a block cell here, we would just keep moving the beginning until we get to something that isn't blocked. So when we hit a block cell, we set the beginning of the section to the point after that block cell. Okay, now we consider this point, it's not filled, it's not a bulb. We consider this point, it's not a bulb, and we haven't seen a bulb before. We consider this point, it's not a bulb, we haven't seen a bulb before, but look, we have this. So this is a bulb, and everything, I'm finding a color I haven't used yet. Everything in this range, from the starting point to the current point, is part of this section. So what it means is that everything in this section should be lit up. And so we can just naively like say all of these are lit up. But isn't that like O of n cubed, right? Isn't that a problem? Well, by the principle of 2 pointers, it isn't, because now we move the beginning of this section to over here. Say, for example, past this point. And so that means that for every time we naively fill in a cell, we also move the purple pointer to the right. So because like there's only n spaces here, this purple pointer is going to move to the right only O of n times, which means that in total we only use O of n time for this row, or O of m, I guess, the number of columns. but each row only takes O of m time. And so here, we continue by saying, we've already found a bulb in this section. So let's just like assume this cell is already lit up because we already have a bulb. And we don't really care about the pointer anymore. And then we say here, we found a bulb in this section. So we light this one up too. And then we hit this block cell. So now this pointer will move over here. And now we can't say we have this bulb anymore because it's blocked off. So now we don't have a bulb anymore. So we go here, there's no bulb, we haven't seen one before, so it's not lit. This is not lit, this is not lit, this is not lit, this is not lit. We go over here. We do have a bulb here. So we would light up this section from this purple pointer to this purple pointer. I guess it'd be to the right. And then all that's lit up, that's fine. We go here, we have a bulb, we go here, we have a bulb, and that's it. That's how we would do a row. And we do the same thing for columns, it's just like swapped. So then that literally just tells us for each cell whether it's lit up or not. And by the argument of 2 pointers, each of O of n rows takes O of m time. And it's the same for columns, so the total complexity is still O of n times m. Which is totally fine, because this is 1500. Oh yeah, I use n to represent the rows and m to represent the columns, it's the same thing. Like n equals h, m equals w in terms of terminology. Specifically not these. You have a lot of constraints here. Okay. Yeah, so that's basically how that would work. You do this 2-pointer strategy for each row, for each column. This allows you to determine whether each cell in the column or row is lit up by something else in that column or row. And then you just count the number of lit up cells. That's the answer. Alright, F. I love F. F is great. F is very weird. So I imagine. Right, how do you do this? The other question is how to explain this. So it's something like this, I guess. So 1, 5, 10. So let's say A1, A2, A3, just for notation and for more generality. And we can even say like AI minus 1, AI, and AI plus 1. And you can consider it to be just these numbers if you want, if you prefer working with examples. So there's some weird constraints to these possible sequences of numbers we can use. Let's assume we're gonna add the numbers to the current number y in increasing order, which makes everything convenient, I think. Maybe it doesn't, but that's how I see it. And that it's rather nice, so you can think of it that way. Oh god, I'm tired. Okay. So we think of it that way. Still recording, right? This whole thing was worth it. Better have been. Okay, so first of all, if we use enough 5s to make a 10, then we could have just made it, then we could have just used the 10 instead of the 5s. So in general, say we take ki of each number. So we take ki minus 1 of this, we take ki of this, we take ki plus 1 of this. Then ki times ai has to be less than ai plus 1. Because otherwise we can use these numbers to make ai plus 1, since ai plus 1 is a multiple of ai. So we can also say it like this, ki is less than ai plus 1 over ai, which is an integer, like by definition. So that's one constraint. And in fact, we have even more restrictions of ki. but they're like weird restrictions. Okay, actually, the cool thing about this is that it means that, like, say we have some number x that we've made out of this prefix. This whole number x is going to be less than 10. Because if we consider it like this, we know that the number of 5s we use cannot make a number bigger than 10. Which means that, like, the number x we currently have is going to be less than or equal to how would this work? It would be that, like, if we've made a number x with this prefix, assume we can have multiple numbers here, for example, then, like, this number y, the number y that we use for the number of 5s, which is the same as ki times ai, is less than or equal to 10 minus 5, or a3 minus 5, I plus 1 minus ai specifically, right? So for, how do we think of it now? So y plus ai is less than or equal to ai minus 1, or ai plus 1. Let's substitute something else in. Like, by definition, x is going to be less than ai. And the way to, like, show this is kind of like inductively, where we start from the beginning and then we apply this inequality, like, iteratively until we get to the point of ai. So, like, by some sort of inductive proof, we can show that if ai minus 1, if x is less than ai, then x plus y will be less than ai plus 1, right? And, like, this is just obvious, because if x is less than ai, then, like, obviously this inequality is going to be true, and because this is less than this is also, this left-hand side is going to be less than the right-hand side. So it's like induction, and we can use the base case to, like, figure this out, because the x for the first element is 0. So by this sort of weird induction thing, I don't really use induction much, which is kind of cool. Essentially the idea is x is guaranteed to be less than ai. What this implies is that, like, there's going to be no, like, we want the number of distinct values of y, which is kind of annoying because there could be overlap. But what this implies is that there isn't any overlap. Like, because none of these numbers could possibly sum up to y, the number of y's we take is completely independent from the sum of these numbers. So what it means is that this subproblem of the first I elements, or the first I minus 1 elements, and the subproblem of the first I elements are kind of independent of each other. And we can solve this and, like, solve this, like, differently. Or it's not exactly that they're independent of each other, it's that, like, in this sort of subproblem, all we care about is the number of solutions. Because there's not going to be any, like, overcounting or undercounting, since there aren't any duplicate values that we'll get. So the number of distinct ways to choose the numbers that sum to y, like this output y, is the same as the number of distinct values of y. So now we're counting the number of ways to form different values of y, instead of specifically the number of different y's, which is more easy because we can do that with a pretty well-known approach called dynamic programming, which I'm actually going to cover tomorrow, so I think that's going to be fun. But the idea now is, like, this prefix is kind of mostly independent. It's mostly independent. So if we're to define some DP state, it would contain the prefix, which means it would say, what's the solution for the certain value of I? Okay, but that's definitely not enough. Because, like, obviously we care about the value we have here. But if we make a DP state for every single value, like, it's just not going to work. Consider a sequence of powers of 2. Like 1, 2, 4, 8, 16. You could literally get every number up to, you can get every number up to 31. Or even like 32 or whatever. But the point is, if we made it based on the sum, like the previous value of x, it would be way too much. There's no way we'd be able to compute that in time. So there's got to be a smarter way, and indeed there is. Let me figure out how to justify that smarter way. Because my intuition is different from, like, the stuff that makes sense. Actually, I'm going to put this in a box since this is important. Now I'll move this kind of off to the side because it's less relevant to what we're doing now. This is me stalling to figure out how to explain this. Yeah. Hey. Alright. So the idea is we know more about this sequence already, like straight off the bat. Because not only do we have this condition, like there's more. Say we have the number 9. Okay. So if we're going to take, for example, 3 ones, so we have 8, or we have 3, then like there's going to be some like issues with like the change, however that works, like the delivering the change, because we have to not have any of the same kind of coins that we gave. So if we kind of do it like this, then we have problems. What kind of problems do we have? There's a lot of stuff going on in the background here that I just kind of figured out and then didn't really think about. So that's why this is hard to explain, I suppose. But why did I undo that? Say we do take 3. Then, and if that's all we take, for example, and like 9 minus 3 is going to be equal to 6 or something. If we take 3, consider 9 the value of x modulo the next value. So specifically it would be, I'm going to get rid of this notation now because it's kind of confusing. I'm considering this value of x, the input value of x. So the input value of x modulo ai plus 1, the next value. Or this would be ai now, and this would be ai plus 1. Totally changing around my notation. So in this case, it's 4. Right? So like these are not equal, clearly. And that means that there's going to be some change. And because everything else is a multiple of this, like everything beyond this number is a multiple of it, and this number is 0 modulo ai plus 1, that means that like the only coins that can be used to dispense this change is going to be coins in this suffix. And specifically it's going to be this one because this is the biggest coin that we have. So like that's the problem that we something we can do. Like, the problem is that we're going to both take some number of coins from this and give out the same, like, give out change with that coin. How do I do this? It's a good question. Like this, right? Yeah, okay. So that's a problem. So that's something to consider, that we need this to kind of be at least very close to this value. It could be greater than. It's like very, very weird. But it definitely can't be 3. It's got to be like, if we don't take any of these coins, then we don't care about the change here, so that's fine. If we do take some of these coins, then it's got to be like the same amount, so that we could use a bigger coin or a multiple instead to give the change out. So either we use this or we don't use anything, is essentially the idea. Or another possibility is that we take something even bigger. For example, this, where x mod AI, if x mod AI plus 1 is specifically greater than 0, and actually let's say we change this number to, okay, this is a very bad example. Let's say we take an example like this. What would it be? It would be 1, 3, or something, and then x equals 5, maybe? How would this work? 4. How would this work? I'm considering some special case here. Yeah, x equals 4. And then say we took none of these. Then we could take more than one of these as long as we make sure that the change doesn't go here. And it would instead go to some number here. Which would mean that if all of these numbers are either used or like the current number we have modulo this number is equal to 0, then the change is going to be forced to come from like this coin. So we can't do that. Okay, I don't think any of this is helpful. So I'm just gonna, at this point, I'm just gonna explain the idea and then we'll like justify it, kind of, I guess. So the idea is, basically you store this flag. So if we consider AI, and then the prefix of AI minus 1, and then everything ahead of it, AI plus 1, then we're going to solve for this prefix. And f can be one of 3 things. If f equals 0, then the sum of this prefix, let's call this s, then the sum of this prefix is less than x modulo AI plus 1. So what it means is like everything we've done so far is kind of too small for x. If f equals 1, then the sum is exactly equal to this residue. Which means that like the idea basically is we want to figure out if we can get away with not using one of these. And that would depend on if this is greater than the number, if this is like big enough that we don't need to use one of these. So f equals 2 would mean that s is greater than x mod AI plus 1. Right? Okay. And we can define AI plus 1 at the end of the sequence to just be some massive number, or like x itself, or some number like 3 times x, which doesn't restrict us in any way. It's kind of lenient. But like, how does this work? How do these transitions work? Let's say we have a prefix that's less. Then what can we do? What can we take for AI? If we take none of AI, then... Oh, and also this assumes that the change like works out for this prefix. Like this is a valid prefix, and that it's not invalid with the constraints of the problem. So this DP also kind of works inductively in the way that like we show that it's still valid. If the previous prefix is valid, then this new prefix could also be valid. Okay, this is not going well. So say we take 0. I'm going to use the number ki to represent the number we take. So ki is equal to 0. Then what happens? Well, the change still remains valid, which means we can do this. And we remain less than because like we haven't added anything. Of course, we're still less than the prefix. Or we can take ki equal to this. Actually, can we? Is the question. I don't think that works. That was the problem I had before. I don't think that transition works. Because like, why doesn't it work? Because it would still cause problems with change, I guess. Yeah, actually, you can't take that because it would cause problems with change. Like, you would end up giving the same amount that you just took from the sequence, and there's no point in doing that because that just screws you over in terms of change. So you don't want to take exactly AI plus 1 over AI. What you might instead want to do is take a number bigger than that. And that like goes with the case I showed earlier, where all of the change will be left to the earlier coins because it's not big enough to have AI be part of the change. So all of the change will be left to earlier coins. And because this is less than, like there has to be at least one of these numbers that we haven't taken anything for. And therefore we can let the change be represented as like some of these coins. So the other possibility is that we take AI plus A of I plus 1 over AI, quantity plus 1. And then this will make it so we're bigger than this. Or actually, it's not, actually no, it's not specifically this. Sorry, we don't take that. That doesn't make sense. What we're considering is this, x mod AI plus 1. So, yeah, that transition was wrong. What it really is we take x mod AI plus 1 plus 1, provided that it's valid, that is, this number is still less than the requirement. And then this leads us to be greater than this, because we just like took a number bigger than it. Actually, it wouldn't just be this. It would be like the number of AI we need to take to be bigger than this. Which is to say, it would be the floor of this divided by AI. It's the number of AI we need to take to get a number like this. And then added 1 because we need to make it so all of the change is going to be in previous numbers. And then with that, we end up being greater than this because we just took more than it. That's kind of confusing, but these are the only possible transitions. So essentially, in DP notation, that means that, actually, I'll sum all of this up later. For now, let's continue transitions. So now we have equals. What happens here? Well, we could again take nothing. And this becomes either less than or equal to, depending on the value of this. If this is 0, then it stays equal, and otherwise it becomes less than. So that's a special case that you should consider, if this is 0. You can see the special case in my code. It's actually very simple. You just like add up all the values, because no matter what, all you can take is 0. So it's just like one addition for everything. And there's also this possibility where you could change from less than to greater than. And otherwise, you could take ki equals this, the same thing, x mod ai plus 1 over ai. Which would mean that ki times ai is equal to or less than this. Except, like, we already know that the previous prefix is going to be equal to the residue of this. Like, because the previous prefix is already equal, multiplying this by ai and then adding it to the previous prefix will make this whole prefix equal. Which means that this is also going to stay equal. It could be very possible that these numbers are both equal to 0. Again, that would be the special case where this requirement is equal to 0. Okay, and the other case is greater than. So either we take nothing, and then this is either it now becomes less than if this value is greater than 0, or it stays greater than if this value is equal to 0. And otherwise, we take the same amount. Actually, can we do that? I think we can, right? Yeah, because like we already know that the change is going to work out like before. So if we take this, then it's kind of like we're just ignoring this number essentially. So the change is still going to work out. Change being in the context of the problem. So this stays greater than. Again, if these two numbers are equal, if this is equal to 0, then we don't do both. But anyway, that is how the transition works. And there's nothing else we can take. If we take a number bigger than this, or a number less than it, then we're screwing ourselves over in terms of change, and the sequence is not going to be valid. Except for in this case, where it is, because all the change is left to smaller numbers. That's where this comes from. We're trying to make it so the change doesn't contain coins that we already used. So if you want motivation for these transitions, I guess you can also check out the screencast. I'm not exactly sure. I don't know how to explain how to get this. I mean, it seems quite arbitrary, I would understand. But it's just motivated by the idea that we want the change to be valid. So if we combine these transitions, we get this kind of recurrence that dp of I and f equals 0 is equal to, well, we consider all the values where it's less than, so it would be these. In the general case, it would be dp I minus 1, 0, plus dp I minus 1, 1, plus dp of I minus 2, or I minus 1 and 2. Just all the possibilities, because all of them, you can take nothing and then end up less than again. Or you can do dp of I and 1. In this case, well, there ends up being only one case, actually. Like, it's just the previous value of equal, because you just stay equal. Again, this is the general case. If these two are equal, then it's like, actually, it's the same thing. No matter what, this is equal to that. So actually, this is always 1. Okay, yeah, this is... I just realized this is always 1. So that's cool. So this actually isn't necessary at all, because this is always 1. Alright, whatever. Well, that makes it slightly less complicated, but... Nice. So then this... If this transition is possible, then it's dp of I minus 1, 0, plus dp of I minus 1, 2. And again, all of this depends on if this is 0. Otherwise, it's a special case. If you want to see how the special case works, you can just see the code. It's kind of like tedious to explain everything, so I just won't. That's the idea. That was right? Yeah, it's sort of easier to handle this like special case stuff by... I prefer doing push dp instead of thinking of recurrences like this, where instead of having this as the sum of all of these, you kind of like push this value out to everything. So this value would be pushed to this one, and it also affects this one. And then you would only push it if it like is valid for the transition. And you would do the same thing for these other ones. Like this one will be pushed out to this one and this one. So that's the idea. And the base case is everything is 0 except for dp of 0 and 0 is equal to 1. Or dp of 0 and 1 is equal to 1. You can think of it like that. Because if you have no elements, then the expected value of the prefix is 0, and you have 0, so it's equal. Yeah, that is so messy. That is the idea behind this code, though. And the answer is, first of all, you can always get x itself by just like the way these numbers work. So the answer is 1 for x plus it's essentially the sum of dp I2, where like, how would this work? This might actually be wrong. How would this work? No, it wouldn't be. It's the sum of dpi2 over all points where ai plus 1 is greater than x. Because that means that you can use ai, you can use some combination of ai in the previous elements to make x by the constraints of the problem. So it'd be the sum over all these, because all of these possible ai could be like the biggest number you use, and so it would be the end of the sequence. And we specifically sum up 2 because we want things that are greater than the prefix, and the prefix would be x in all cases where ai plus 1 is greater than x. That's the convenience of using this like greater than thing, because we're literally just counting the numbers greater than x. But then also to make sure we don't overcount, like it's it's like my convention would just be to set these values to 0 if ai plus 1 is greater than x, because we don't want to use any more values that are greater than. We don't want to overcount. And also, any other values that are greater than would immediately be invalid sequences if you extended them. So it's easier just to set them all to 0 and count them all as invalid after you add them to the answer. Oh boy. Okay. Well, I hope that was like in some measure understandable. I feel like it wasn't, but I don't know. If it's still confusing, I'm not entirely sure. Possibly watch the screencast to figure out where these ideas come from or something. Like the motivation behind these transitions, because they are kind of obscure. Also, these are just implementation tricks. But yeah, it's kind of all I have. I'm not sure how to explain that better. So that was ABC 182. I didn't end up full solving. I do have all the solutions on here, kind of. Yeah, that's all I got. Goodbye.